I'm Anna Beltseva again. I teach at NYU and Brooklyn College. Brooklyn College is my main campus for many years. I graduated of Brooklyn College and CUNY Graduate Center is an Earth and Environmental Sciences PhD program. But my research has been always involved soil, and I teach soil at Botanical Gardens. Some of you are my former students. And now I'm just spreading a word about soil sciences on social media. Some of you are my Insta followers as well. And I think since this, in this current situation where botanical gardens and other institutions are closed and we don't have classes, so I decided to spread the word about soils through other avenues. So today we'll talk about factors of soil formation, rock cycle and weathering, soil formation in general, how it forms. We talk about transported soil and what's the difference between clay and sand, effect on soil chemistry, why rocks are important and minerals and what they do to soil. And then I'll wrap up and take home message and give a few minutes for Q&A. Is what we have on our clothes, on the fingernails when we work in the garden, something that stays behind. It's outside of the soil and just soil particles. While soil is alive, it's an evolving body, it's constantly changing. It's full of living organisms. We have more organisms in a handful of soil than the people on this earth. And it's how this looks under microscope. It's really, really diverse. And we don't even see or even know all the organisms in the soil. It takes really long time to form the soil, up to 500 years to form an inch of topsoil. And soil provides nutrients, and it's what we will talk today. We will see how this formation process takes place. What is soil? Soil is made of particles, minerals particles, 45%. In ideal soil, it's of course, if we go different landscapes, we'll find different proportion. But if we take average ideal soil, it's 45% of minerals, which takes the majority of soil. Air, 25%, water, 25%, and the remaining 5 gives organic matter. And this organic matter comprised of organisms, with decomposed organic matter, roots. One of the most important soil properties that we study is the soil texture that comprised of sand, silt, and clay, and they come from rocks and minerals. So you see this microscope view of a soil with some minerals, and here's the soil on a larger scale. If you dig a pit of soil and look down, you will see different layers. But how we get to this point? How soils form these layers? And why? This is New York City soil. This is soil from Brazil. And why there's no layers here? So what's the difference? What are the processes behind it? Few other my favorite photos. It's New York City as well, and you can see here how soils are diverse. They have different colors, they have different layers, different particle sizes, different formation. Some of you will form by glacier streams from 10,000 years ago when we had glacier here in northeast of the United States. Some of them by wind deposits or lake deposits. Some of this is a coal ash or construction debris or sand dredged from the Hudson River in deposits in Brooklyn. So they have different parent materials. So now let's look at factors that form soils. So soil, on another word, is pedosphere. Scientific word for soil is pedosphere. And pedosphere comprised of soil, air, we already said, different gases, biosphere, plants and animals, live or dead. All organic matter in any kind of state, it's part of organic matter. Soil water, of course, we have water in the soil, and it can be in a different stage or different amount, but for the most part, there will be always presence of some molecules of water on the different scales. And lithosphere, rocks and minerals, they take up the largest proportion of soil, and it's 45%, as you already know. So the interaction of all these spheres make up pedosphere, and it's important to remember. That's why soil is not dirt. And what factors affect the soil formation or soil profile development, the examples you already saw? There are 5 factors: parent materials, climate, organisms, topography, time. In an anthropogenic world, in urban environments, in even rural environments, when we have input of human anthropogenic input, people affect these factors, and this will affect pedogenesis. Pedo means soil, genesis, origin or development. So the formation of the soil or the origin of the soil. And we also have practices, weathering practices, I will introduce you in a few slides, and different soil formation practices like additions, the leaves falling from the ground, on the ground, losses, gases that live in the soil, or erosion, transformation of rocks and minerals, or organic matter that breaks down or decomposed in the soil, translocation, it's materials that are moving within the soil by gravitation, evaporation, or soil organisms. All these factors and processes will affect soil profile. And different stages have form different horizons or different layers in the soil. So we start with the rock. Again, 45% of soil made of rocks. And this rock is just a bedrock. It's a rock that it's breaks down, it disintegrates under heat, temperature, wind, snow, like frost, sunny day. It all affects the rock. Then pioneer plants will start growing on top of this rock, like lichens or mosses, and they will disintegrate chemically these rocks further and releasing acids to the soil. These acids, organic acids, or due to their respiration of carbon dioxide, and this carbon dioxide combines with water in the fragmented rocks, will eventually form carbonic acid that helps to dissolve these rocks even further. And over time, this dissolution takes place more and more. Plants start growing further down, the roots, the succession, new plants will come in, and they will break down the rock further and further down. So soils are forming from the top, bottom. And you see at the end, we will have rich organic matter from all this dead and decomposed organic matter on top. There will be different layers forming, and at the bottom, we'll have a bedrock, the original rock. And we will come back to these layers and see what actually they mean. So again, the soil formation factors are parent material, topography, climate, organisms, and time. We will mostly work on this today on parent materials. So rocks and minerals. Rocks are made of one or more minerals. I'm sure you know it from your earth science classes, but just to review it. And minerals that make rocks, they are naturally occurring in organic solids with a specific chemical composition and atomic or crystalline structure. Igneous rocks. These rocks are formed from crystallization of magma. And this magma can solidify, cool down and solidify underground, or it can be exposed on the surface from volcanoes, and it becomes lava that will cool down, solidify, forming rocks, and eventually it will form volcanic soils. Metamorphic rocks are rocks that it's either igneous rocks or sedimentary rocks that due to tectonic processes brought under the earth, like really underground, very deep, and under heat and pressure, they metamorphose, they change chemically or physically, and they become different types of rocks. And sedimentary rocks are rocks that are just fragments of other rocks that over time were moved, transported to a new location, deposited there, and after some compaction and cementation, they become new types of rocks. And I will give you a little bit more examples. So why these rocks are important? If you look at this graph, we'll see that this is the abundance of elements in the earth crust. So oxygen is the most abundant element, followed by silicon, aluminum, iron, calcium, sodium, potassium, magnesium. These common elements found on Earth crust, we see that iron, calcium, potassium, and magnesium are plant nutrients. So plants require for their growth. That granite is an igneous rock. It's a common building material. But did you know that granite contains 14 out of 17 essential plant nutrients? So plants only need about 17 plant nutrients. They don't need all 90 or 100 that's on the periodic table. They only need 17. And 14 comes from a granite. And the minerals come from this granite is feldspar, the quartz or some mica, but feldspar will eventually form clays, and we'll come back what clays are. Sedimentary rocks, I'm sure you're familiar with limestone or sandstone. It's sandstone is formed from sand. It's silica and oxygen, those two common elements on Earth. And silica is everywhere around us. It's the most common element in soil. Limestone is calcium carbonate. It forms from shells precipitated at the bottom of the ocean. And calcium, again, it's a nutrient. We need it and plants need it too. And also it gives high pH to the soil. Metamorphic rocks. This a representative of marble. Limestone under heat and pressure will become marble, and it's the same chemistry. It's calcium carbonate. So calcium will be given to the soil. Plants will take it, but also the presence of limestone or marble will give high pH to the soil. So you may not grow blueberries in that type of soil. But how these rocks and minerals break down and become part of soil? Due to weathering. Weathering can be mechanical, physical, or chemical. During physical weathering, by temperature, wind, water, rocks crack and they become fragmented over time into smaller pieces, and they then transported by wind and water down the slope and have a new deposition. Chemically, it's changed due to water, typically hydrolysis. It's called reaction with water. And when minerals is dissolved over time, or some elements are dissolved from this, from a rock or mineral. So chemically and physically, these rocks can be broken down to smaller pieces, transported to new locations, or just dissolve and become ions that eventually plants will take as their nutrients through the roots. So mostly around the world is actually transported. It's not local. It can be transported by different agents like wind, by glacier, by water, even like in the lakes or in rivers, streams, even organic deposits like in the marshes or wetlands. It's also, all these deposits will form soil. I'm in New York right now, and most of you, I think too. So you know that we have a glacier deposits. 10,000 years ago, the glacier brought all this material on its way from like Canada practically, and stop in the middle of New York, and we have this amazing topography and amazing diverse soils. So in the US, since where at the moment we have parent materials that are, you see, it's very diverse. The US is very diverse, and we see the different sedimentary rocks, the igneous rocks, Rocky Mountains, there's some marine deposits. Here's the glacier drift. You see it's like the northeast. There's some, what's this color, very pale, alluvial and colluvial, so it's brought by streams, by rivers, fluvial deposits, by wind. So this parent material deposits or rocks that form the US is very different. It's very diverse, it's very heterogeneous. And this is why soils in those locations are also very different, right? Because it's inherent properties of the soil. Because if you have this parent material that is quite different and diverse, and we will have also diverse soils. So how specifically soils form. We already saw this sequence, right? So I want you to see it again. The rocks, bedrock will be occupied by pioneer organisms, mossins, lichens. Eventually they will disintegrate, break down rock, and the roots of other plants will grow deeper, deeper, and deeper. They will break down, they will die, they will accumulate this organic matter, and eventually have this beautiful layers of soil. This process is very slow. It may take like at least 100 years to form 1 centimeter of soil. It depends on where we are, how warm, how humid it is. Different landscapes, different climates will have different speed of soil formation, but it's very slow. And it's so important to manage our soils properly and remember that they're fragile. Dig soil in your garden when you get a chance. Please do. You will be amazed by this diversity of colors, of textures, of soil organisms, and how it all changes as we go deep down. So you will, if you dig down, you will see, well, if you dig down like 6 feet, that you may see these different layers. And again, it depends on your landscape, where you are, how young or old your soils are. The older the soil, the more horizons you're going to see. So this is a very well developed horizons, an example. And if soils are very young, you're not going to see all these layers, and they're not very distinct. So this is the ideal soil profile. Again, not all soils may have it, but we'll look at this ideal situation. We have O horizon on top, A horizon, E, B, C, and then bedrock or unaltered parent material. So O horizon is typically presented at the very top, and depending where we are, it can be very thin, it can be absent, or it can be very thick. If we are in my hometown in Russia, we have very deep organic layer because of the fibrous grassland roots. If you're on the Great Plains in the United States, you will see it as well. If you're on a tropical rainforest or any other forest, you may see only organic litter on top, not much in the soil itself. So O horizon, it's organic horizon. A horizon, it's organically rich mineral horizon. It have lots of minerals, broken down minerals, by what we would consider as dirt, as soil, but also there will be some organic matter because roots grow in this A horizon, and they will break down and form this, help to form this layer. E horizon, it's the layer when or where actually nutrients are leached down due to gravity. It's a layer of losing the components, and they're leaching downwards into the B horizon. And this is B horizon where these nutrients from above, they will accumulate. E horizon is very distinct by its lighter color. If you dig down and you see very distinct light whitish color, that's probably your E horizon. And then the B horizon is it's where things accumulate. You'll see lots of clay may precipitate from layers above. C horizon is an altered, or actually altering parent material. It's not rock anymore, but it's not very rich in organic matter. So it's a mix of broken down minerals and soil, but not much of organic matter unless roots can grow down. So how is it related to the nutrients? So now we looked at the processes, right? So like we saw different stages, how rocks and minerals, well, which first of all rocks, minerals exist. Then they break down. We know there's a weathering processes. We know also they're transported. But then what does it mean for our plants? For our plants, it's super important because plant nutrients, plant nutrients like vitamins for us, they need these nutrients to get from soil. And there are four pools of minerals where plants can take it from. The number one long-term and very abundant pool of nutrients is actually soils. It's or soil minerals, I would rather say. Soil minerals are a major source of soil supplied nutrients, and it's at the longer term storage, meaning that rocks and minerals, they will take time, really long time, years, hundreds of years, even thousands of years to break down and release those nutrients. But it's the largest and the longest term storage pool of nutrients. Another pool of nutrients I should mention is organic matter. That's why you add compost, and you know, like organic waste will be broken down within months and release nutrients during this process. Absorbed nutrients, the ions attracted to humus, it's a well-decomposed organic matter in the soil, and clay particles. They're typically available for plants, and that's also why you add compost to the soil, because those nutrients are readily available. And dissolved ions. So ions in a solution, if you don't remember from chemistry, ions is like, it's your salt that you put in a soup, but you feel the flavor of saltiness, but you don't see salt anymore, right? So those are the ions. So salt was the mineral halide that you had, white crystals, but when you dissolve it in a soup, they become ions. So those ions is what plants take up for their needs, and the nutrients have to be in ionic form in order to be uptaken by plants. So if you have a piece of rock growing right here, and the rock and the plant is here, plant cannot directly take it from the rock. It has to break down, it has to dissolve and become ions. So that's why it's the longest and term storage of nutrients, but it's important to have it. And fungi, we'll learn in future webinars, or they're super important because they actually can mine minerals from, actually nutrients from minerals and rocks, and deliver it to the plant. So that's why rocks and minerals are important, because fungi can help us to get those nutrients to plants. So a little bit of chemistry and geology, give you some ideas. I know some of you love rocks here. So you already know this minerals, rocks, we mentioned them. So like we have, this is granite, and the quartz or feldspar come from granite. They're very common minerals on this earth, but they commonly come from granite. And quartz will eventually become sand and silt, and sand, silt, and clay is what makes mineral portion of the soil. Feldspar will eventually chemically can break down into clay. Mica, these flaky minerals you see in your soil very often, it's also it can become sand, silt, or clay, or chemically it can crystallize and form clay. I will give you an example how that happens. Some other common rocks or minerals, actually, pyroxene and amphibole, they can also form sand, silt, and clay if they break down into smaller sizes. But if they chemically weather, they can become clays or oxides. Then some other salts that can be found in breakdown, like, you know, maybe gypsum, calcium sulfate, or magnesium sulfate, they dissolve in a solution in water present in soil, and they release calcium, magnesium, potassium, sodium, and some other ions that are necessary for plants. And carbonates, limestone, dolomites, they can also give calcium and magnesium to the plant and to the soil, of course, bringing up pH level at the same time. Okay, and then, so I mentioned sand and clay, and the people sometimes, well, you already, most of you answered correctly that clay is the smallest particle size, silt is the medium, and clay is, sand is much greater. So sand is the largest. You can actually see it with your naked eye. It's like, I compared to the brown sugar. You can see it, you can feel this grittiness. Silt is in the medium. You can feel it, it's like it's smooth flour between your fingers, but the clay, it will stick between your fingers. You cannot see it, but you feel it's sticky. And what is important to remember, that clay is not just the size. Clays are also minerals. So sand silt is referring only to the size, large, small. We can give the gradation, like in millimeters. But clay is not just the smallest size, but also there are groups of minerals that are called clays. And vermiculite, probably you use it for your garden, or like in house plants. But you also know kaolinite, if you ever did like a vase, like pottery, the two different types of clays that you already know. But there are different type of clays, different climates. We find different clay types, and it's something I wanted you to differentiate for yourself. So clay is the size, but also clay is a mineral. So how this mineral form? It's typically due to some chemical weathering processes. So let me show you. So sand and silt come from primary minerals like feldspar, mica, quartz, while clay, they will go to this primary minerals. They will break down, feldspar, again mica, but then there will be chemical stage that will create clay. So let's look at this stage. So again, our primary minerals, we call them feldspar and mica. They will weather down, they will break into smaller pieces. They will dissolve in the soil, in a solution, in the water present in the soil, just like our salt in soup. It becomes dissolved ions. We don't see it. If you wanted to measure it, we would measure it just like taste of salty soup. But over time, they will crystallize again because it's concentrated. The solution is concentrated with ions. They will crystallize and form secondary minerals. So this stage is chemical, right? It's not physical anymore, it's chemical, it's crystallization from the after dissolution process. And we will have different clays. And depending where we are, depending on which landscape we are, different climates, we'll have different type of clay. First of all, carbon, hydrogen, oxygen. Those are the most common elements that in organisms, in our human or plant or animal bodies. So they are essential for us, of course, because they're building blocks, but they're non-fertilizers. We cannot run out of oxygen, hydrogen, or carbon, okay? So they're building us, but it's not like we can lack of them. So it's not important to add them as a nutrient. Nitrogen, phosphorus, and potassium, those are macronutrients that plants require in large quantities. And they need it for for enzyme activation, for DNA, for RNA, for ATP, for like different energy. So they play a big role in soil for plant growth. Calcium, magnesium, sulfur, they are considered as secondary nutrients because they also required in larger quantities, not large as macronutrients, but more than micronutrients. You'll know them, calcium, magnesium, sulfur, they're very common mineral nutrients. Micronutrients, boron, chlorine, copper, iron, manganese, molybdenum, zinc, sometimes nickel is added, but sometimes not. Those are elements that are required in small amounts by plants. And they are just as important as macronutrients, but they need to be in small amounts. Otherwise, they become toxic. They very quickly can become toxic. Some other elements that plants may need is sodium, silicon, and cobalt. Some plants we need it, not most of those plants, and that's called beneficial elements. And all these elements, all these nutrients that are necessary for plants can come from rocks and minerals. They can also come from organic matter, but it's a topic for another webinar. So here I wanted to highlight these elements and nutrients that come in, except for nitrogen, they will come from rocks and minerals. Nitrogen is a different story. It's the largest pool of nitrogen is in the atmosphere, not in the earth. So the inherent take-home message, and I'll take your Q&A. It's there are about 17 essential elements that plants need. Most of these elements are coming from rocks and minerals. They absorb from the soil, but for these rocks and minerals become available, they need to be dissolved breaking down and then dissolved to ionic form so plants can take it unless fungi help them to deliver it. So rocks can prevent soil erosion. So if you have pebbles or gravel in your garden, it's actually beneficial because it will hold the soil in place. If you just have loose organic composted soil that I see a lot in community gardens in New York, the soil can be blown away. If you're on an open field, like an open garden, like on, I don't know, Long Island, you'll have to add compost, I don't know, every month. It will be just blown away, it's loose. So it is important to have these minerals because they will hold your soil. It's wiser to have minerals in the soil rather than just plant in the compost because you will have to do more management with that case. These minerals and rocks, they will eventually give nutrients to your soil. They also improve infiltration and drainage because they create larger pores in the soil. So the water, instead of like running over or just going too quickly, they will actually stay in the soil for longer and prevent erosion because there is no runoff. Water will go down. And to have a little bit, you don't need a lot, definitely not a lot, but up to 15% is a good number of this gravel in the soil. It really will help to prevent the erosion, especially if it's like on open spaces. So I always advise to learn about your soil, test, diagnose, and treat your soil. You can be your own soil doctor.